kids, and welcome back. We're still primarily on review mode with just a little bit of, some new stuff implanted in between. A key difference between pre-AP chemistry and AP chemistry and IB chemistry is the ability to explain why and go a little harder in terms of the mathematics. But primarily that difficulty is in the explanations. Now, we did electromagnetic radiation when you were in pre-AP chemistry. We did these calculations. I want to refresh your memory, but I'm not going to do any calculations in the video because I don't think you need me to model this. I want you to just remember some of the terms. We're typically going to be talking about waves typically all the time in using the speed of light as the velocity of the wave. And the wavelength is the distance in meters, centimeters, or nanometers, or you'll see down here a new unit called an angstrom. And that is given the Greek symbol lambda, and you can measure that, in a variety of ways, just so you get a whole trough and a whole crest of the wave end. So this would be your wavelength. Now, frequency would be as if you had a detector. I'm just going to kind of draw a little eyeball there, detecting, like maybe you were on a street corner and you were counting the number of cars that went by in a particular amount of time. In this case, we are counting the number of waves that go by in a particular amount of time. And if the cars were bumper to bumper, if you had a big car, so as you increase the wavelength, fewer cars would go by in a particular period of time. If we had bumper to bumper Mini Coopers, like I drive, that means a shorter wavelength, more Mini Coopers would pass in time than, say, a stretch Hummer limousine. So remember that these are inversely proportional. And for those of you who just got out of physics, I want to show you that physics, whoops, that didn't change the color, but that's okay. Physics typically uses an F for frequency instead of the Greek letter nu. Go figure. We just want to be a little bit different from one another. All right. Now, when you do these calculations, and we have to study this, or we want to study this, because we're going to find that the mathematics of waves was very helpful in fact, fundamental in helping develop the quantum mechanical model of the atom. Additionally, one of my favorite topics in chemistry, to do research again, this is what I did research on and I would do it again, is the area of spectroscopy. And that's the interaction of electromagnetic radiation with molecules and atoms. So it's pretty fascinating. To do these calculations, just watch your units, all right? If the meters and nanometers you see in meters, that one would be given to you. I prefer to memorize this one because nanometers is such a common unit for wavelength. Just make sure that your units for lambda and C match. Now, frequency is 1 over seconds or seconds to the minus 1. There shouldn't be an issue with that. I've never come across a problems where somebody put frequency in minutes. Energy is in joules, the SI unit, and Planck's constant is another constant that was developed. We talk about energy acting like a particle as if it's a little particle called a photon, and that photon has the energy h nu, and that's Planck's constant after, of course, a dead guy. Now, when you do this, something that's really tricky is you'll be talking about, let me erase and get some room here, is when we have these joules, we would have joules per photon. So if you have joules for every one photon, you may have to calculate that in the world of moles, and so we would have to get rid of photons and go to moles. Well, how many of anything is in a mole? Well, 6.02 times 10 to the 23rd. So there's 6.02 times 10 to the 23rd, or Avogadro's photons per mole. and that way your photons would cancel and you would end up with joules per mole. So that's also a common calculation that you'll see with these. And we'll do some more in class in case your memory is not as good as I would love it to be. All right, this shows the electromagnetic spectrum and the different frequencies that you have. This is radio waves down here at the end. And you're talking about tall buildings. I like this picture. I found it on the internet. I don't think it's copyrighted. As you get into microwaves, we're talking about humans and into butterflies. Infrared radiation, that's what you see for heat. If you ever have somebody want to evaluate your home for heat linking, or those night vision goggles that visualize people at night, are based on infrared radiation. Visible light, the wavelength is roughly the size of, say, an amoeba or something like that. When we're at ultraviolet light, we're talking about a molecular level of size, and X-rays are now at the atomic level. So that's a good one, I think, for you to be able to work with. And let's take a look at this. This spectrum, this part of the spectrum here is your visible, and you should remember Roy G. Biv. You don't have to know the particular wavelengths of those, but you should know the relative position. Infrared is below the red. Ultraviolet is above the violet. And the other thing this shows is that wavelength and frequency are inversely proportional to one another. Now be careful. I've seen pictures in which the whole scheme is flipped. So this is low frequency, this is high frequency. I've seen ones where that's reversed. So watch your scales carefully on graphs. Now the other thing is that energy is directly proportional to frequency. So energy would move with frequency on this. Now, let's take a look at the types of spectroscopy that we would do on this. In our spectroscopy, if you're talking about the TV radio waves, we're talking about something called nuclear magnetic resonance. It's what an MRI is based upon, if you know anybody or you've had an MRI. And that studies nuclear spin. Not all nuclei have, what we call a spin. I don't want to get into that too much, so I want you to just accept that term. But it's a little bit like we talk about electron spins. And so we look at changes in the nuclear spin in the presence of magnetic fields. And that studies molecular structure. Those of you who are in IB, you'll get to study that in more detail, and it's a very, very cool topic. I added that for completeness. AP is going to focus on these and knowing what the ranges are. If you're in the microwave, it's studying rotational spectroscopy. Molecules can rotate. So if we have a hydrogen and a hydrogen, that molecule can simply rotate. And it doesn't take much energy to do that. You can think of yourself in bed. It doesn't take much energy to roll over in bed. In fact, you do it in your sleep. You don't even think about it. It's just a low energy movement in bed. So that would be in the microwave range. Infrared is critical. That's what I studied in graduate school. IR, you may see the term FTIR. That adds a mathematical component called Fourier transform infrared. Just does a mathematical operation on the spectra. And then Raman spectroscopy. This is an absorbing technique. This is typically going to be a scattering or emitting technique. And it's really cool because I got to use lasers. What we're studying with that are bond vibrations. Now, infrared is higher in energy than microwave. Molecules vibrate. So if we could take a look at this molecule here, not many ways that hydrogen can vibrate, but it can stretch, certainly. So the analogy you can think of is yourself. You've now woken up and you're stretching in bed. That certainly takes more energy than rolling over does. Okay. Now the next one is UV vis. We will actually get to do this. These you simply have to know the ranges. We will perform experiments on this, and this involves electron transitions. So UV vis spectroscopy and atomic emission spectroscopy, and it's going to be the movement of electrons within. So this is the movement of electrons within an atom or molecule. The electron hasn't left yet. So again, back to our analogy, you've rolled over, took a little bit of energy. You're now awake, so you're stretching. UV vis, you got up and you went into the bathroom to shower and get ready for school. Takes quite a bit of energy, but you still haven't left home base yet. You're still at home. X-ray, and we will talk about this later in more detail. We'll analyze spectra from that. And this takes a lot more energy. And in this case, the electron actually leaves the atom. The atom becomes ionized because an electron leaves. So we'd have some atom, and it's going to form an ion plus an electron. So now you've left home, you're on your way to school. That's going to take quite a bit more energy associated with that movement. So hopefully that analogy gives you an idea of how to get these spectra kind of in perspective in terms of energy and an electromagnetic spectrum, because you will be asked questions on that. All right. Now, what we're going to be doing next is delving into finally our actual atomic structure. And so until I get to see you again, this is, as always, signing off.